Jay Rathert is a 26-year employee of KLA. He leads the strategic collaborations with partners in the design, manufacturing, and test ecosystems, where they're looking for new methods to improve yield, quality, and reliability. He started a project a few years ago that started focused on automotive part quality and has grown to include known good die for mobility, high performance, and advanced packaging. Welcome, Jay.
Thank you, and I'll alert the attendees here ahead of time. I am broadcasting via satellite. There'll be a little latency. I'll try and anticipate slide changes, but if it sounds like I'm talking about something you're not seeing yet, give it a second, and I'll try and stay ahead of that for you. First of all, thank you for the invitation to speak here today. I'm a bit of a stranger in a strange land. I think, would you say MEPTEC represents packaging, test, and EDA? So I am none of the above, but what we're hoping to do, I'm very gratified by the discussions we had today from Tomcat and from Mark about this ecosystem and data flowing together. I'm a big believer in moving data across domains, and what we're trying to do is offer the data that we're finding in line during manufacturing at the physical level and see if that helps us make better downstream decisions about what is a known good die. So question number one for those of you who aren't familiar with us, who is KLA? Good question. Why are we in this known good die discussion? Well, for those who know us, historically we've served the fabs. And that group today would be known as our semiconductor process control group. In there we merge advanced optics, high performance compute, lasers, precision machine control to create systems that can find nanoscale level defects at the physical level on all the many layers that constitute a chip today. In the last few years, we recognized that Moore's law was slowing down and we needed to move into the more than Moore space, and we acquired a company called Orbitech, which has brought us into the electronics, packaging, and components area. So we're starting to recognize the impact of advanced packaging on our business and on the industry in general. So that's a big growth area for us. We now do inspection and metrology analysis in the advanced packaging space, as well as specialty process tools, PCB, and flat panel. Just some quick numbers across the bottom. I'm not going to dwell on those, but KLA has grown over my time there from just a few $100 million to now more than $8 billion. And now more than 14,000 employees around the world. Number 5 top capital equipment supplier to the industry. For those of you who don't do inspection and metrology every day, just a quick primer on some of the terminology. Inspection means that we're looking at each individual layer and process step, looking for things that ought not be there. We call those defects. And metrology is a term we use for measuring things that should be there. This could be shape or thickness or composition or resistivity. And these components together are the underlying pillars for yield and performance of the die. So as I've interfaced in my collaborative role and directly face-to-face with customers, I've noticed an evolution in the lines of questioning. I mean, forever KLA's reason for existing would be to improve a fab's productivity by increasing their yield so they can get a better ROI on the materials end by producing more good die out. But increasingly, people are asking us not about just aggregate yields, but about individual die quality. It started in the automotive space, as Ira pointed out, because so many die there are mission and safety critical. And because of the growing content there, the sort of tyranny of numbers that can cause a car to be down. So people are asking us, is this die fit for purpose? Can I trust putting it in my airbag or in my brake controller? But then as we grew into the EPC division that I just told you about, this advanced packaging, and we see the trends there in 2.5D and 3D stacking, certainly the same requirements for quality and known good die are there in spades, with the sort of twin challenges of increasing complexity in the packaging and the uncertainty of testing all those die before they can be integrated into the final package. This is just a simple slide we used internally to help us sort of quantify the problem. Of course, the known good die problem is not new, but but one bad die or interface during assembly can kill the whole package. And just this simple look at the trend on the graph on the right shows an increasing number of chiplets, increasing complexity and increasing cost. And if we use just sort of a simple model, these are some industry models, Williams Brown or Seth Agrawal, and make some, again, just basic assumptions in a simple model of 90% yield and 98% test coverage, then you can anticipate about 2,000 parts per million escaping through test. Of course, your mileage may vary. Every model is wrong. Your model may be different, but this is just a stake in the ground. So then, if we're expecting 2,000 parts per million, even though we're getting 99.8% effectiveness in stopping bad die, there's still going to be a small fraction that are going to slip through. And as we take that small fraction and multiply it, statistically speaking, as the chiplet count grows, just as the packages are getting more costly and more complex, we're going to have increasing yield fallout just from escapes. So the question KLA is asking themselves is, how can we use data with our portfolio today, or data that we need to create with future solutions to help augment this and capture these escapes earlier, shifting left, so that they don't make it out into the packaging step and become a failure at the packaging step. Any questions at that point, Ira?
Nope, no questions so far.
Okay. So again, for those of you who aren't familiar, my goal is not to make you industry experts today, but to recognize what we're doing today, what the current model is, and what the shortcomings are with the current model. The fab tends to think about things in terms of a yield curve, as shown up here in the upper right of this slide. When a device is new at time zero, yields are low, and there's typically a lot of inspection and metrology going on as we solve all the integration problems that are slowing down our yield ramp. And slowly we resolve each of those issues and move up the yield curve until yield peak, or not peaks, but flattens out here in this top part of the curve when we're reaching what we call entitlement yield. And at this point, we're just looking for excursions. Now, if I look here at the graphic in the middle, inspection and metrology typically happens between all of the major process steps. Literally hundreds of points along the building of a chip get inspected and measured. Once we reach that sort of baseline level of yield entitlement, really what we're looking for is just excursions. And to do that effectively, we really don't need to monitor that many wafers. In fact, what most people do is just a small percentage of total wafer lots get monitored, and then a subset of wafers per lot get selected for monitoring. And net on net, usually we're looking at 1 to 2% of wafers in the fab end up getting monitored for this excursion control in a mature fab. And that's perfectly adequate when we're just trying to maintain our baseline and recognize when things have gone a little off kilter. But it's not terribly good for recognizing a known good die. We're not going to see every wafer, we're not going to see every die using this method. So bad die are going to slip through. If we look at it another way, you can think about process control as being sort of this loose grid here on the left. It's well adapted for stopping excursion lots, but individual at-risk die and even maverick wafers can pass right through our visibility. And especially when yields are low, when a device is new, a lot of bad material bangs up against electrical test. And we're hoping against hope that between probe and burn-in and any other kind of final test, we're going to find all those bad die before they leak out. But as I pointed out, there's lots of models out there that say there will still be some escapes. So the question then is, well, what can KLA's role be in this? For our normal fab customers today, their focus is on yield. So this is a wafer probe map that would commonly they would commonly see at the end of wafer production. Mostly what they would care about would be the ratio of green die to red die, reducing the red die until we reach some sort of acceptable economic level and we have enough yield to satisfy our business model. The question is, are all of these, so the red die are going to be inked out and cold out, of course, and not packaged. All these green die would normally go on to be packaged through the line. The question is, are these green die really good die? Are these known good die? And will our methods downstream stop the ones that aren't. And is there data that KLA, again, could augment this decision with? So what I'm going to do here is overlay the defect data for this real automotive wafer and see what it informs us. So what's interesting here is in the upper left, we see some sort of defect mechanism, perhaps a scratch or some other source, where there's quite a high level of defectivity at the 11 o'clock position. So several of these die, which I'll highlight here, have passed wafer probe. And perhaps they'll go on to be packaged. And perhaps they'll be caught later in the process at additional test insertions, or perhaps they won't. But when we talk about shifting left, certainly this type of information would be very useful in determining whether this die is suitable for being in some sort of safety or mission critical role. And what's interesting about it, when I look at this, a lot of process control is focused on maximum sensitivity. What's the smallest defect that could possibly be going on? What's the identity of that defect? But when I look at these die, I certainly don't need that level of granularity. They're defective enough that just by themselves, I can see that they're outliers from the rest of the die on this wafer. And can I somehow capture that information in a faster way on every wafer in the fab? So that led us to this idea of revisiting screening. Screening is different from process control, where we subsample. Screening implies that I will look at 100% of the wafers, 100% of the die, but maybe not on every layer. Couldn't really practically do this with the hundreds of process steps that are going on in building a chip. But when we ask most of our fab customers, do you know which layers are usually your reliability critical ones? Most of them rattle off 4 to 8 key layers. So certainly with the right approach, it's practical to implement a screening solution there. Screening is not a new concept. It's been around a long time, but there have been some hurdles in the past that has slowed down its adoption. Number one is economics. The system needs to be fast enough to cover all of your wafers in process or WIP at multiple layers at an acceptable cost of ownership. And then the data quality has to be good. If the data quality is no good, then no cost is cheap enough. No economic solution will be suitable. So we have to address 3 different problems in the data quality. Number one, underkill, which means that the system has to be sensitive enough to recognize bad die and see all the defects in them. Number 2 is overkill. I don't want to throw out good die and waste yield. And number 3 is be actionable. Inspection data is inherently noisy and voluminous and complex. So we need some sort of cleaning and distillation and normalization solution to make it usable. It needs to be customizable, and it needs to be shareable in this open format that Tom and Mark talked about. So we ask ourselves, is there a single metric that KLA could create that would simplify and make this data actionable? Any questions so far, Ira?
Nope. I think actually you may want to mention for people who aren't familiar with the concept of a maverick wafer.
Maverick wafer is just like this one highlighted in the red box in the lower right. All the other wafers are somewhat in control, but something dramatic is going on in this one wafer. And certainly it would be good to know downstream that that has happened so that I can have forewarning and treat it differently at test. If not, just cull it out of the line altogether. Okay. So designing a solution. Again, my goal here is not to make you an expert on KLA systems, but just to help you understand what our method is and help you see that there's potentially credible solution that could provide data to you. So we call our solution IPAT, which is short for inline defect part average testing. And like the name might suggest, it started with a concept of statistically recognizing those outlier die, like the scratch I showed you in the wafer. So we borrow from part average testing, the idea that this die is maybe within spec, but outside the norm for its population. So then we had to design it on a viable system that was fast enough. So we built it on our very fastest wafer inspectors, and then added the latest advances in machine vision and AI to do recognition. And then it had to be stable enough to be trained by an expert user and then left to run autonomously and do all the die disposition on its own in a trustable way. and then output a simple aggregate score for each die that downstream users could put to work. So I'll take you through those steps just sort of briefly so you can understand what's going on under the hood. So on the left, I just show sort of a cartoon of an example die. And there can be lots of different defect types going on a given layer. These are shown in cartoon format here. But one thing to understand about defects is that not all defects are created equal. Their type, their size, and their location has a big impact on how they're going to affect the die. A small defect in an open area may have zero impact at all. Bigger die in a patterned area like this could create shorts that will definitely kill the die. And then there's some that may be uncertain, like these mouse bite chunks out of a line that may become reliability issues over time. So the machine vision of the system is measuring all the physical attributes of all these defects in runtime as the wafers are being scanned, and extracting basically a digital thumbprint of each and every defect. At the beginning of implementation, these thumbprints are trained by an expert user who categorizes them into bins, either defects that will very likely kill, defects that will probably have no impact, or ones that were uncertain, and then assigns some sort of weightings to each one of those bins. So that it looks something like this. These red ones are definitely the high priority defects that I'm most likely to kill. The green ones are probably not going to be any sort of impact. Maybe they'll be cleaned off, maybe they're too small, or maybe from history I know that they won't matter. And the orange ones are uncertain. And now the expert can apply some sort of weighting to them. So we'll call the red ones today, for our example, 50, the orange ones 10, and the green ones 1s. So this is happening for every die, every wafer, at runtime, with no SEM review. The machine vision and AI is assigning these bins. So now let's look at what happens in production. Let's follow this one die off a wafer as it transitions through, in this example, 4 reliability critical layers. On layer 1, I found one sort of mid-risk defect. On layer 2, 2 mid-risk defects and 1 low-risk defect. Layer 3, 1 definite killer defect, and layer 4, 1 mid-risk level defect and 1 low-risk level defect. And when I weight those, 1, 10, and 50, as I did before, I can get an aggregate score for this die as it moves through production. In this case, 92. So the iPad system will monitor each of these inspections as the wafer moves through every wafer, and each die will begin to build up an aggregate score as it moves through the WIP. When I look at the entire population, what we'll see is a distribution of die scores. Across the top here, you can see just 5 sample die. Here's one that's highly defective, lots of killer defects in it. We're going to score this one 175 using those weightings I just pointed out. Here's a die at 64 and 61. And on the other end down here, here's a really low defectivity die with only score of 2. So with these aggregate scores, now I can take a statistical approach. Each die in the population can then be put into a Pareto format, with that IPAT aggregate score being the height of the Pareto bar, and each bar here representing an individual die in the population, either on a wafer, in a lot, or in a multi-lot sample. Then using JDEC limits, I can set multiple limits in the iPad system, so I can treat die differently depending on where they fall in the population. Some die in this example are clearly outliers and should probably be culled right away. They're extremely defective. Other die past the shoulder have some defectivity and maybe bear different treatment. And then still the third category are very low defectivity die, and maybe these could be considered known good die. All this data is then exported into an open format, which we call the industry standard CLARF 2.0. And that data can be then shared with the downstream testers or with any kind of outlier detection software algorithms that exist out there. What the iPad data at the wafer level ends up looking like is something like this. Here's a wafer with 4 different layers of iPad data using examples like I just demonstrated to you. Most of the die on the wafer come up green, nominal. They have very low defectivity. A few of the die that you can see here are marked in red, This is what IPAT has labeled as outliers based on the user's customizable limits. And several other die are sort of in that mid-range, that uncertain range, in this case, orange, that bear closer scrutiny downstream. So IPAT data can be either, that score can be disaggregated. You can look at it front end versus back end, or by layer, or by die region, or you can look at the total score in aggregate or all together. What's interesting about this now is that this data format is relatively friendly from an IP standpoint. So we believe fabs will be more likely to share this data than they would if this was just a full defect wafer map, which most fabs consider to be very IP sensitive data. So just a quick case study in the few minutes I have remaining so that you can see how this is working. We've been at this for several years now. It's installed in 5 fabs in production. We started with automotive IDMs and it's spanning out from there, and it is now a released product. Here's an example use case from one of those fabs. Again, I'm going to show you a Pareto. Each one of these tiny blue bars represents the IPAT score for 500 of the worst die out of a population of 100,000. So 0.5% of the total population. So again, there's 99,500 die off to the right. And I've truncated the y-axis here because some of these had very, very high defectivity scores in IPAT. So now what we're going to do is overlay the test data. A die that failed any test, either probe or burn-in or final test, is going to be coded red. And any die that passed all electrical tests is going to be coded green. So the first thing you note is that most of the die that IPAT said were outliers went on to fail electrical test. And that's good. That's good. That means we're an independent source of correlated data using just defectivity. The defectivity data matches what test is finding, as you would expect. It just means the system is doing what you would expect it to. But what's interesting is these 32 other die. These are 32 of the most effective die in this population out of 100,000. And yet 32 of these went on to pass every test and to move into the supply chain. These are certainly not die we want in our airbags or in our brake controllers. Certainly not what we would call known good die. In a second use case, here's again a broader population, not the wafer level, but in a 76,000 die population. And again, you can see it in 3 different segments. On the extreme left, you see die that are severe outliers in the defect domain. And these should most likely be scrapped right away, representing cost savings in the packaging and removing some risk from the population. Because most of these die will overlap with tests, the incremental yield loss is trivial. On the right-hand side, we see the very low-risk die that had very few defects in them, just 1 or 2 across all the layers inspected. So maybe these are our KGD candidates. And this middle population, the at-risk population, well, this depends on your use case and your end customer and what his needs are. Excuse me. If known good die is important to you, we might elect to move the red portion to encompass all of the orange portion and scrap all of these die. Or maybe they can be binned or repurposed, or maybe burn-in will suffice to put these die into the supply chain. Excuse me. Excuse me. So in the end, we think that you get a better known good die estimate by merging the IPAT scores with test scores. So if test is showing good and IPAT score is good, perhaps this is a better designation of a known good die than what exists today. If IPAT shows bad and test shows good, it's probably best just to scrap this die now and save packaging costs and save the cost of additional test insertions. And where there's ambiguity in test, maybe IPAT can be the final arbiter, or at least a factor in arbitration of whether this die should be good or burned in or scrapped outright. Well, while this vision has been successful so far in IDMs, we have definitely encountered some challenges that I would like to, perhaps address in the panel, where the folks who implement this, the inspection and metrology folks, are a long way from the folks who care about test insertions and known good die. And their common metrics of success are just yield. And as long as the ratio of green die to red die at wafer probe looks good, they're happy. So the question is, how can we help them see the win in the fab that you care about at end of line, whether that die is going into an automobile or into an advanced package. And I'd be interested in hearing Tom's ideas and Mark's ideas and maybe some of the other questions and ideas from the audience here today about how we can continue to break down these barriers and share valuable data to help do a better job of recognizing known good die. Thank you.
Yeah, thank you, Jay. There's some questions here on the case studies. I mean, so the ones
Sure.
like the first case study where you had the scores and the ratings, those are purely based upon the optical inspection, right? If you go back to the first case study.
Yes, we are not training based on test. This is trained purely on the expertise of the defect experts in the fab and their experience of years of making wafers and other devices, and ultimately feedback from RMAs and from yield. Generally, they know which die matter and which locations matter most, and we adopt their scores and then compare that aggregate score versus test.
Okay. And for these, I think you said 32 parts. Were these dies then further tested, or how did they do? So they passed all the electrical tests, but did they then get burned in? Were there any
But this
RMAs
includes burn in, but not system level test.
Okay. Okay. And did they?
So this was a dedicated study. This was a dedicated study where we were watching them all the way through, so that we had extensive background data on SEM review and the images, the layers, the defect types, and then compared them each step to validate the concept. So more data here than you would have in a usual HVM implementation.
And these 32 die, after you guys were done, did they do any additional tests? Did they ship them, or they just scrapped them? I mean, what did they?
No, they scrapped them. They're building confidence in the iPad score as a shift left method to go ahead and scrap them out now. And some of the defects, actually a lot of the defects, when we went hunting for these, we thought we were looking for tiny little latent defects. And shockingly, a lot of the defects in this population were big particles, big shorts, big opens, misprocessing areas like dishing, where the die was obviously going to be dead. So I think we were very surprised at the size of some of the defects that can make it through.
Okay. Well, so let me put on my hat and look at this cross-functionally. Did the test engineers then get assigned to figure out why these passed tests?
Actually, I think what you pointed out is just another great application for this, both to improve the process control plan in the fab. Why didn't we see ones that failed tests that we passed, and improve the test plan, especially as a device ramps? I think there's a lot of synergy between these two methods going forward.
Got it. Okay. And then you talked about the case where you were comparing the test results to the IPAT score results, and one of the viewers asked, "What's an example of an ambiguous test score?" You in that matrix,
what's my example of an ambiguous test score?
Yeah.
So sorry, that's not my area of expertise. I'd have to defer to the test experts, but I know that it certainly seems like if you have analog areas and things like that, it's not always cut and dry whether a die should be released or not.
Right. Okay. Well, thank you, Jay, for an excellent presentation. I want to thank everybody once again and wish everybody a good rest of their day. So thank you, everyone.